Looking at section P.6, part 2. This time we're going to look at what happens when we are simplifying our rational expressions, but we don't have the same denominator. So a little review on finding the least common denominator. In this case, we're going to step 1, factor each denominator completely. Step 2, list the factors of the first denominator. Then we're going to add to the list in step 2 any factors of the second denominator that do not appear in the list. And then step 4, we're going to form the product of the factors from the list in step 3. This product is the least common denominator. So what happens when we're adding and subtracting rational expressions that have different denominators? We need to, step 1, find the LCD of the rational expressions. And so step 2, we will rewrite each rational expression as an equivalent expression whose denominator is the least common denominator. To do so, multiply the numerator and the denominator of each rational expression by any factor or factors needed to convert the denominator into the LCD. Add or subtract numerators, place the resulting expression over the LCD, and if possible, simplify the resulting rational expression. Let's try one. So for example, we're going to subtract rational expressions. So if I look at my first fraction, I have an x over x squared minus 10x plus 25. And I'm going to subtract from that the x minus 4 and a 2x minus 10. So step 1 tells us to find the least common denominator. That means we need to look at each denominator and factor them. So the first fraction, the x squared minus 10x plus 25 denominator, if we were to break that down, that would be a square double squared. We'd have an x minus 5, and I'm just going to write it out side by side as another x minus 5. If I look at my second denominator, I have a 2x minus 10. Well, what's in common is a 2, and we're left with an x minus 5. So we can clearly see we have an x minus 5 kind of in common. So our least common denominator, we're going to have an x minus 5 and an x minus 5. X minus 5. They said to list out what was in the first fraction's denominator and then add to it anything that was missing from the second. Well, we already had that x minus 5. We also need that 2. And remember, numbers always go in the front of your factored out form. So now from here, step number 2, we're going to write equivalent expressions with the LCD as denominators. So now we're just going to take and rewrite this problem using our least common denominator. So we have a 2 times an x minus 5 and an x minus 5 as a denominator. We're going to subtract from that. I'm just going to rewrite each of these fractions separately. So again, we're going to have a 2 and an x minus 5 and an x minus 5. So just like what you would have done with any regular fractions, once you change that denominator, you have to change the numerator. Well, if my first denominator was an x minus 5 and an x minus 5, what else do we need to get to a 2x minus 5, x minus 5? Well, we would have had to multiply by 2. So that means that x has to be multiplied by 2, which is going to give us a new numerator of 2x. When I look at my next one, this was a 2 and an x minus 5. Well, I already have a 2 and an x minus 5. The piece that I'm missing is an x minus 5. That means I'm going to need to take this x minus 4 and multiply by an x minus 5. And I'll FOIL that out. So we're going to have an x squared minus 5x minus 4x is a minus 9x. A minus 4 times a minus 5 gives us a positive 20. And now that I have my two fractions set up with least common denominators, now I can, step 3, subtract the numerators and put the difference over the LCD. So if I were to take a look, I have that negative sign kind of hanging out in the front here. So I need to make sure that I'm subtracting all 3 of those pieces. So technically, I have a 2x minus x squared. So I have a 2x minus x squared minus 9x. Sorry, this is going to become a plus 9x. And a minus 20 when I hand out that minus sign. So minus x squared plus 9x minus 20. That's all over top of our denominator, 2 times x minus 5 times x minus 5. And if we go about subtracting, let's see, we're going to end up with, we have a negative x squared, highest power first. I have a 2x plus a 9x, which is going to give us a positive 11x. We have a minus 20, and that's all over top of 2 times x minus 5 times x minus 5. And the last thing it wants us to do, it says, if necessary, simplify. So I might try to double check that numerator. If I try to factor out that negative x squared minus 11x plus 20, is there anything that's going to multiply to make 20 and add to make 11? 1 and 20, 2 and 10, 4 and 5. It doesn't simplify anymore. So that means I'm going to end up with that as my final answer because I can't simplify anything else. And if you remember, we also had to state what our exclusions were. Anything that would make x not work in this case, well, all I have on the bottom in terms of factors is an x minus 5, which means that x cannot be equal to positive 5. So I'm going to go ahead and erase this little piece over here because that was just my double checking that there's nothing else I can simplify. So the next type we're looking at is what happens if we have complex rational expressions. So a complex rational expression, also called complex fractions, have numerators or denominators containing one or more rational expressions. A complex fraction must be simplified so that neither the numerator nor the denominator contains any rational expressions. This is where we get into fractions in fractions and they look really ugly. Don't panic. All right, so for example, they want us to simplify. On the top of that fraction bar, we have a 1 over x plus 7, and then we're taking away 1 over x, and that whole thing is being divided by 7. So it says we will use the method of multiplying the numerator and denominator by the least common denominator for all rational expressions. Says the least common denominator for all rational expressions is, so if we were to take a look, the ones that have the rational expressions, we're pretty much looking at the denominator of the numerator, if that makes sense. We're looking at that x plus 7 and that x. That's what we really need to get rid of. So what we're going to do is we're going to take this and we are going to look at what's in common. Well, nothing's in common, but the factors that we have are x and we have an x plus 7. Those are the two pieces that we need to make a common denominator, or LCD. So if we take the fraction that we're given, we're going to end up multiplying this by the number 1. That means we're going to multiply by x times x plus 7 over x times x plus 7. That's going to help us eliminate those fractions and fractions. Those denominators, x plus 7 and x, are going to help us kind of cross-cancel some things out as we go. So to have a little bit of room to work, we're going to continue this process down here. What this means is we are going to multiply this x plus 7 with this piece of fraction and that piece of fraction. And then obviously the one on the bottom is going to multiply with the 7 that's on the bottom. So we have a 1 over x plus 7 that has to multiply with this x plus 7. Then we have a subtraction sign, and we're going to take our 1 over x, and we're going to multiply that again by that x plus 7. And on the bottom of that fraction, that's why I said we want a little bit of room to write, we have the 7 that's going to multiply with the x and the x plus 7. So all those just kind of get smushed all together because it's just multiplying. Let's see what we could do to simplify this ugliness down. Let's see. We have an x plus 7 that's going to cancel an x plus 7. So 1 times x is going to give us x. We have minus. This x is going to cancel that x. So we have a 1 times an x plus 7, which is just x plus 7. And on the bottom, we have a 7x times x plus 7. So now if we go about simplifying that, I distribute out that minus sign. So I have x minus x, which cancels out x. So all we have left is a minus 7, which is going to be a negative 7. And on the top, we have a 7x and an x plus 7. Anything else simplify? Well, yeah, we have a 7 and a 7. So that's going to leave us with just a negative 1 on the top. And we're left with an x and an x plus 7 on the bottom. And we need to make sure we state any exclusions. X cannot equal 0, and x cannot equal, that would have to be a negative 7 to make that factor a 0. And that's our final answer for that ugly, ugly problem. Fractional expressions in calculus. It says fractional expressions containing radicals occur frequently in calculus. These expressions can often be simplified using the procedure for simplifying complex rational expressions. So let's take a look at what happens when we have some radicals involved. So it says we have the square root of x plus 1 over the square root of x, and then we're dividing by x. Again, we don't want a fraction in a fraction, so we look at that denominator. We need to get rid of that square root of x. That means we're going to multiply by the fraction square root of x over square root of x. Hopefully you understand when you multiply by a number divided by itself, that's equivalent to the number 1. That's how we're able to do this. So that means if I'm multiplying this top of the fraction by a square root of x, and the bottom of a fraction gets multiplied by square root of x, we're going to do a little distributive property. Distribute this out here. So square root of x times the square root of x, just for the sake of seeing what we're doing, we'll write that out. And then if I take an addition sign, I have that 1 over the square root of x, which multiplies by a square root of x. And then on the bottom of my fraction, we have that x times the square root of x. So we simplify this down. Square root of x times square root of x, that's just going to give us x. 1 over square root of x times square root of x, well, those two things cancel, which is just going to give us a plus 1. And then on the bottom, we have an x and a square root of x. Now this is also where it gets a little tricky. This is an x to the first power. This is an x to the 1/2 power, which means in the end we end up with an x to the 3/2 power on the bottom and that x plus 1 on the top. Now in terms of exclusions, we might be able to only have to worry about that x equaling 0. So as long as x does not equal 0, because that's the only thing that would make it divide by 0. And one last little piece. Rationalizing the numerator. Just like we rationalize denominators, we could also rationalize the numerator. It's helpful later on when we are simplifying some expressions. We need to simplify it down a little differently or look at it a little differently. So it says to rationalize the numerator, multiply by 1 to eliminate the radicals in the numerator. Just like you would rationalize the denominator, same concept. We're just going the opposite direction. So we multiplied the numerator and the denominator by the conjugate of the numerator. So our last example, rationalize the numerator. We have a square root of x plus 3 minus a square root of x, and that's all being divided by 3. So they want us to undo the square roots on the top. That means that we have a subtraction sign in between. That means we need to multiply by the conjugate, which is going to give us the addition sign. So square root of x plus 3 is going to add with the square root of x. And what we do to the top, we're going to do to the bottom. And we know when we multiply by the conjugate, the inside-outside terms cancel out. So that means that we're just going to end up with the square root of x plus 3 times itself is going to give us an x plus 3. A square root of x times the square root of x, we're just going to end up with a minus x. And on the bottom, we have a 3 times the quantity, square root of x plus 3 plus the square root of x. And simplify it down just a little bit more on the top there. X plus 3 minus x, the x and the minus x is going to give us just a 3 left on the top. And we have a 3 times all that nonsense, which, do you see what else we need to simplify down? The 3's also simplify, so that leaves us with a 1 on top of the square root of x plus 3 plus the square root of 3.